Hi, my name is Fateh. I'm a PhD student in the Department of Electrical Engineering, and today I have the honor of having a discussion with Professor Green, who is a professor of power engineering with a research focus on the analysis and technology to develop a zero-carbon electricity supply system that is dominated by variable renewable sources and other inverter-based resources such as battery energy storage. He is also academic lead for sustainability, and in that role, he works to make the university's own activities sustainable by dealing with carbon emissions from our energy use, carbon emissions from goods and services we buy, biodiversity, air quality, and many more. He's a fellow of the Royal Academy of Engineering, the Institute of Electrical and Electronics Engineering, the Institute of Engineering and Technology, and the Chinese Society for Electrical Engineering. His work has been supported by EPSRC, National Energy System Operator, NESO, SSEN Transmission, and Hitachi Energy, and he works in collaboration with ESIG, ESIG, and GPSD. Thank you for joining us, Professor Green.
Thank you, Fateh.
Yeah, I really admire your work and the extent of research you've done. I think you completed your PhD 34 years ago.
Thank you for the reminder.
And so, but what makes you passionate about research, and why this area of research?
Yeah, it's interesting you split those two things. So I knew when I finished my undergraduate degree that I hadn't stopped learning, and I wanted to do a PhD for that reason. It wasn't a grand career scheme. It was just I wanted to carry on learning, and I hope I've never stopped. Essentially, there are challenges and there are intriguing things just from an intellectual standpoint. You know, I wonder how we're going to solve that problem. Okay. And people sometimes characterize research as either applied or theoretical or fundamental. And I think it's more subtle than that. And my approach is what I hope is application-led fundamental research. So there's an issue we want to address. For me, at the moment, it's decarbonisation of electricity grids. And it's not just collect the best technologies and put them together. It's what are the fundamental questions that we have to try to answer before we can reach that goal. And I find that inspiring. The challenges around climate change mitigation, so getting off burning fossil fuels for electricity and for industrial processes, is compelling. We are beginning to see weird weather, I think is the phrase I quite like, and you get more weird weather the higher global average temperatures rise. Mm-hmm. So that is a repeated reminder, and the fact that we now have extraordinarily challenging government targets on decarbonisation says, this just needs to be done. And on the other hand, we know there are things going on in electricity systems which are hard to model, hard to explain, hard to know how we're going to control them, hard to know how we're going to stop using some of the features of gas-fired power stations. So, I'm not finished learning, and I hope I'm making a contribution that actually has some impact in the way this country addresses decarbonisation.
Definitely. I think you are. You spent a lot of your focus. Your prior focus was on power electronics circuitry and HVDC, and then you moved to the more system level approach. And what informed that transition?
So it'll be a history lesson if I'm not careful. I started doing power electronics just because I found it interesting. I had a tutor in my second year of undergraduate degree who was in that area. Mm-hmm. I had an industrial placement that summer that was also in that area, and so I sort of fell into doing a PhD in the area. But it's all about controlling motors, controlling their speed or their torque or their position or something. So intellectually interesting, not particularly inspired in terms of application area. Okay. I moved to Imperial College, and there were people around me doing lots of grid studies. It wasn't quite always framed in terms of decarbonisation, but it looked like the next frontier for power electronics, and that's how I got into power electronics for power systems, either as microgrids, which were quite popular at the time, or high voltage DC, which by and large is about decarbonisation because it's about connecting to big offshore wind farms. It's what the UK needs to do to decarbonise, connect to big offshore wind farms, by and large. And I think more recently, inspired by kind of some of the things our colleague Mark O'Malley has set up around the Energy Systems Integration Group and the Global Power System Transformation Consortium, really thinking through what does it mean to run an electricity grid at, let's say, 100% renewables. It might not be quite that. It might be some nuclear or something else in them, CCS or whatever, but very high fractions of renewables. And that just opened up so many technical challenges, and it feels a bit like what it must have been like in the 1960s when electricity grids, which had already been around for, let's say, 80 years, started to get much bigger on a national scale, and things started to go wrong. Generators oscillated and shafts snapped, and oscillatory modes were discovered that no one had foreseen, and a whole load of maths had to be developed to predict that and to tell you how to mitigate it. And we're going around that loop again, because now we don't have big synchronous machines. We have lots of inverters with their own sets of dynamics, which present challenges, and just fascinating. And knowing you're doing a fascinating thing, which also helps decarbonisation, that's great.
Yeah, it makes it worth all the effort, because research can be a daunting task and a very long-range effort at times. How do you answer those who question the premise of our work? For example, the entire idea that the global temperatures are rising, the sea levels are rising, and it is because of carbon emission. I think there's a lot of dissenting opinion about that. People who argue that global temperatures have always been rising, and the potential rise in sea levels is not as catastrophic as we make it to be. I mean, there are entire books written about this, right? And then they're highlighting it seems like the targets set by governments all over the world are quite aggressive compared to the pace of the technology, right? So there's a mandate for EVs, for example, but then the technology to make it as convenient as fossil fuel-driven vehicles is not yet there. So there are just questions about this. I don't think I've heard a very academic response to it. Can you say
there's a lot in there. Help me out if I don't tackle all of the points you raised. Look, I'm not a climate scientist, so I can't unpick the climate science off the top of my head, but I know climate scientists on this campus and deeply respect their work, and there's almost no dissent in the academic community and the research community and the Meteorological Office in the UK and the equivalent bodies throughout the world. They agree, and that climate change is happening, global temperatures are rising, weather systems are changing as a result, and that it correlates with rises in CO2 and other greenhouse gas present in the atmosphere, and that although the climate has always changed over Earth's history over millions of years and tens of thousands of years, the rapidity with which it's changing now just correlates with the steep rise in CO2 concentrations that started with the Industrial Revolution in the middle of the 19th century. You can see the global average temperatures and the data on CO2 start 1,000 years before the Industrial Revolution, and then see the rapid uptick when the Industrial Revolution kicks off, particularly as it starts to really gather pace in the 20th century and become a global phenomena more than kind of a Northwest European phenomena. So I have to leave that there because that's not my specialist topic.
Okay.
You mentioned other things about the ambition of the targets. In a way, we have no choice but to have ambitious targets. If we don't, we already miss several ambitious targets, but if we don't get global emissions on a downward trend now,
it will never happen.
It will never happen, but we'll also hit extreme temperatures, mid-century 2050 and end of century 2100. And that's too terrifying to contemplate. We've seen, it's hard to attribute individual events to climate change. There's some very good work at Imperial that attempts to do that on a statistical basis. But you saw what happened in Valencia, close to a year's worth of rain dumped on that city in 24 hours.
Wow.
And there's no drainage system in any city anyway, could probably have coped with that. Severe flooding and more than 200 people killed. And we see changes in the extent of desert systems in Sahara and elsewhere. We see evidence of the changes, and extreme cold events in places like Texas, which are not used to extreme cold events. So we are seeing the evidence, and I think making sure people are given the way to think about that, those events become more common under climate change. They can't say each individual event was caused by it, but they are getting more common. So we have to bear down quickly, and of course, climate change happens because of the amount of CO2 in the atmosphere. So just because you stop emitting CO2 doesn't mean the climate gets better. The climate just stops getting worse. So we actually have to start taking carbon out of the atmosphere and other gases. There's a big emphasis now on emissions of methane from the oil and gas industry, leaks from pipes, but also releases from wellheads and other things, deliberate or not deliberate. And of course, methane is 60 or 80 times worse than CO2, but it's shorter lived. So it only exists in the atmosphere for maybe 100 years, where the CO2 will exist for many hundred years. So complex things. You mentioned electric vehicles. There's a bunch of technologies we know, solar panels, wind turbines onshore and offshore, batteries, electric vehicles, heat pumps. And so we have to build a lot of it, and it used to be very expensive, but it really isn't anymore. The cost reductions in solar power have been absolutely extraordinary. From the 1970s, when it was only really used on satellites, because that's the only way you could get energy in space, almost, it's tumbled from things that cost, I don't know, hundreds of dollars per kilowatt of panel down to $1 or $2, and very low cost of energy.
More than 90% reduction.
Massive reductions. And we are seeing wind follow a similar trend, and batteries follow a similar trend. And how does that happen? Because every time you manufacture these things, you learn a bit more about how to manufacture them better and more cheaply. And because you, as a manufacturer, anticipate your competitors are learning how to make them cheaper, you work really hard to make them cheaper yourself. So innovation is driven in those industries like that, where you are turning out high volumes of product, and what differentiates you from your competitors? Cost, so you drive down cost. And in those technologies you can. So, famously, nuclear energy doesn't follow that trend. You build occasional nuclear power stations. There's a lot of upfront engineering.
Yeah.
Almost inevitably, everyone is different from the last one because safety regimes moved on or technologies change. So you don't build many, and then you don't build them all the same, and you don't get the same cost reductions.
Yeah.
We can debate, and maybe you want me to later, whether small modular reactors change that picture or not. So it's no longer the case that you have to subsidize some of these technologies. They just are a cheaper way of generating electricity. And maybe electric vehicles and heat pumps, because of the way taxes fall on petrol, gas and electricity in not entirely sensible ways, the economic case is not quite so strong yet, but it will get stronger.
Yeah. It seems to be a very multifaceted problem, and very interesting and applicable too. And I think so. Your work at Imperial has two sides. There's the teaching and research, and then leading the sustainability efforts.
Yes.
I'm tempted to ask, which of these you think is more difficult? Because you devoted 50% of your time to either one.
Yeah. Well, they're quite different, so the comparison is not straightforward. I think helping a university, an organisation as big and as complex and diverse as a university, to slash its carbon emissions. So our target is no Scope 1 and 2 emissions by 2040, and to bear down as hard as we can on Scope 3 emissions, which is embodied carbon in goods and services. The target on Scope 3 is a little bit vague, but we will be shortly revisiting our strategy, and the target next time will be firmer because we've learned more about exactly how to calculate our Scope 3 emissions. And until you can calculate it with some degree of authenticity, it doesn't make any sense to have a target anyway.
Yeah.
Anyway, so that is hugely challenging because there are so many dimensions to it. And the dimensions are quite different to each other, and it requires the university as a kind of a corporate body to dig deep financially and in terms of other resources, to change our buildings so we no longer have to put as much heat into them to keep them warm, and then to change where we source our heat from gas boilers and CHP engines to ground source or air source heat pumps or some similar low zero carbon source of heat. It's going to be tough, it's going to be very expensive, it requires mobilizing the resources of the university, and it means scratching heads very hard about how do you completely change the thermal insulation of a building when it's absolutely critical to our operations that it's
daily
packed full of students and staff. So where do we decant people to while we do deep refurb of their building? So there are no easy answers to that. And then there's scope 3. So what are people buying to use in their labs? What reagents in chemistry labs or whatever, materials for various testing in civil engineering, mechanical engineering, whatever it is. Can you do your experiments with less material, less reagent? Can you do them in more energy efficient ways, like using your equipment better and running ultra low temperature freezers at a more sensible set point than -80, provided it complies with the protocols for the experiment and so forth. Just thinking harder about what could you tweak that would use less energy or use less material. And then things you wouldn't necessarily think about. We buy an enormous amount of furniture as a university. We refurbish rooms, and the kind of the lazy thing is to throw the old furniture out and buy new furniture. I've been on some site visits to some refurbished buildings outside the university sector where they use reconditioned furniture, and some of it is magnificent. Some of it is classic designs. Wow. So they actually look great because they're classic designs. And the thing about the classic designs is they're often made well, so you can reupholster them or something, or polish them.
They're more durable.
And if you have wooden tabletops, unlike these sort of plastic coated ones, if someone dents it, a small dent in a wooden table doesn't look bad, but a small dent in some modern materials, it glares at you. So anyway, we have to get people off always thinking that the smart thing to do is buy brand new modern furniture. There's a ton of examples along those lines, but then there's travel. And we're a global university. We expect to have global reach in terms of how we recruit students. We expect to have global reach in how we disseminate our research, but also in the partners we work with. So people like me fly around the world. And encouraging people like me to fly less often by combining, if I'm going to fly to the United States for purpose A, can I make sure purpose B, C, and D that are coming up later in the year are taken care of at the same time? So fly less, or how much of that can be done online, or for nearer destination, can you go by train? And I've tried a bit of that, and as I said elsewhere, I've got an unhealthy interest in trains, so I didn't mind spending 13 hours on a train to Switzerland several months ago, because I got to look out the window, lovely scenery, and change to trains a few times. So
it's not a simple problem.
It's not a simple problem, and so let me just wrap that up because I know I've gone on too long. It's not a simple problem because it's behaviour change. It's getting people to understand that all the little decisions they make that maybe are driven by a scientific purpose also have a carbon consequence. And what can you do that doesn't change the quality of your research or the quality of the dissemination of your research, but does massively reduce the carbon? That is super challenging to get right.
Wow. Interesting. There's a lot to unpack there, but I want to get to the center of our discussion today, which is the next buzzword in our field, which is grid forming. I was in a conference last year, I think, in the Wind Energy Science Conference in Glasgow, and the sessions that were about anything related to grid forming were significantly more attended than all other sessions. Like, we literally had to rush to get a seat. And so what is it about this thing called grid forming? Is it just the next buzzword? Is it one of those things that people will talk about for 20 years, but that will not really move the needle? There are many such things like that.
Yeah, and there are many. There are several technologies that pop up which seem to have a good justification to begin with, and then just become an exercise in academic research. They're tricky problems to solve, so lots of people pile in to try and solve them, and it takes a while to wake up and notice that actually industry's not interested, they're not buying it, they've moved on, problems are different. So if it turns out to be that, we have to realise that quickly and get out, because there's no shortage of genuine problems to want to solve. So what is it? Okay, so take the UK example. We have massively reduced carbon emissions for electricity. They've gone from about 150 million tonnes a year down to about 30 or 40 million tonnes, so massive reduction. And it has changed the way we operate the grids, but not massively, because all of those wind turbines and solar panels have an existing grid to connect to. There's a voltage available. The electronics in the interface finds that voltage, identifies its frequency and phase angle, synthesizes a current to inject into it at the right phase angle, and injects power into the grid. So we call that grid following. A grid has to exist, and then you follow it by synchronizing it to it, and then you inject the power, and that's your job done. But it's doing nothing to help run the grid other than beyond the simple job of providing power. It doesn't help control the frequency, the voltage, or any of the other things that electrical engineers worry about. So grid forming says actually sometimes that renewable source that goes through an electronic interface needs to actually form a grid. It needs to be the one that provides the voltage and sets a frequency and regulates the magnitude of the voltage as well, so that other things can synchronize to it. And when we get to the stage of shutting down we've already shut down our last coal plant, Ratcliffe-on-Soar switched off finally at the end of September. We will drive down our use of gas to the point where we will one day switch off our last gas-fired power station. And then what then is setting the frequency and voltage of the grid? It will have to be some grid-forming inverters. So actually we've had grid-forming inverters for decades. I said earlier I worked with microgrids. In a microgrid you have to have something that forms the voltage and frequency of the microgrid, and we've done that with inverters 15 years ago, possibly 20 years ago. But it's now, how do you design a national scale electricity system knowing how much grid forming you need versus how much grid following? Is it a buzzword? Oh gosh, yes, it's a buzzword. Is it a useful buzzword? Slightly more difficult. Yeah, we do need to do something, but I think I really liked your comment about the popularity of sessions at conferences. I saw that in a different conference. It was crazy. They were even, because different committees had all raised different bits, there were even parallel sessions, different sets of panelists. And I think a lot of people latched onto this as the way to solve a host of problems in grids that can actually be solved by other means. And whatever the grid forming converters are, they're not the answer to every problem that exists.
I remember a comment you made some time ago. You said it feels like everybody has said grid forming is the answer. Now, what's the question? So we've decided on the answer already. But so 2 years ago, you contributed towards a paper on a paper that proposed a duality concept for comparing grid forming and grid following, because one of the problems is that what we call grid forming is not a particular thing. It's a range of things, but with a particular concept. Right, and the duality theory proposed in that paper, it already has, I think, about almost 300 citations, which is in just 2 years, and helps to give a better understanding of other aspects of inverter control, like the grid strength, synchronization, that we're more interested in. So could you talk a little bit about how GFM and GFL, that's grid forming and grid following, are duals of each other?
Yeah, sure. But let me just at the top of that say my co-authors on there are more important than me in terms of the intellectual development of that paper. So Yitong Li, Enji Gu, and I think Yue Zhu were three co-authors on that. So great heap of credit to them for the work. I think the interesting thing was, I don't know what the thought process was exactly in retrospect. Partly that actually grid forming and grid following are not that different to each other. They're not. It's not a completely binary divide, and you hinted at that in your question. And the other was when you start to see they're similar but different, you notice they're similar but different in lots of ways, in fact almost always, and then they look like joules of each other. So grid following converter needs to see an existing voltage and it injects current into it, and it's synchronized to what exists. And then in the grid forming case, it's the other way around. You provide the voltage and the current flows whatever the grid draws out of that source.
Okay.
So that's a voltage current duality. One, you form one and the other's a consequence of the grid. Grid following, kind of famously, can we say that, have stability issues. They're more likely to develop an unstable behavior and oscillate and go wild and have to be disconnected if the grid is what we would call weak, which is relatively high impedance compared with how big the inverter is. So on the end of a long transmission line that has a lot of inductance and resistance, they will tend to go unstable. So the answer to that is grid forming, except you have to be cautious because the grid forming tends to go unstable at the other end. If there's not much impedance between it and the next grid forming converter, then it goes unstable because just the duality of the way in which they synchronize, and it's a loss of synchronization behind that instability. And one goes one goes unstable on a high bandwidth and the other on a low bandwidth in terms of the synchronization loops. And different behaviors under fault conditions, so just in parentheses, power cuts are rare because, not because faults don't happen in electricity networks, but because we have redundancy built in, so you can lose certain pieces of equipment that's still carrying on. But we also have protection systems that notice when something's faulty and get it off the system in less than half a second. So they have different behaviors during a fault. So the important thing is that while a fault is happening and is in the process of being cleared, so that half second or something, the equipment stays connected and is available as soon as the fault clears. And they behave in opposite ways in that process. So I think that was what was fascinating. That once you spotted they're kind of equal and opposite in one dimension, you start to realize they're equal and opposite in lots of dimensions. And then that gets you a deeper understanding of how they behave. And actually, although it doesn't come very clearly from what I've just said, it also teaches them there's more of a continuum between them. Yeah. So it sounds a bit odd. They're joules of each other, but you can imagine intermediate points between them also.
Yeah. So I think there were five categories in which they were found to be presented to be duals. In terms of just synchronization controllers, the GFM uses a frequency droop control. A GFL synchronizes using the PLL. And grid interfacing characteristics, like you described, the GFM is a current following voltage forming. It just forms the voltage and lets the current flow based on what the grid can draw, while the GFL is the other way around. It follows the voltage and forms the current. And in terms of swing characteristics, the GFM has a current angle swing, while the GFL has a voltage angle swing, and inner loop controllers and grid strength compatibility. So but you mentioned something about you want to say something?
No, I was just thinking, well, you remember my paper better than I do, so that's nice.
I reviewed it some time ago when I was going to attend the summer school on grid forming controls, which was in Lille, France, last year. Yeah, so sure. It's I think it's a very good material. It's a journal paper, so it's very holistic. So I found it really good.
Thank you.
And concerning the frequency droop and PLL duality, it was presented in the paper that the GFM uses the power frequency droop control, and because the power is directly proportional to the d-axis current, so it's also kind of d-axis current frequency droop control, and that can be represented as a current phase synchronization. So it's almost like a PLL, but instead of taking the q-axis voltage like it is in the GFL, it takes the d-axis current and then it's a current synchronization, and then it looks like
so it's sort of D to q-axis and swaps between voltage and current. So it's a duality.
And then from the GFL, the VQ synchronization can be represented also, I think, with the reactive power synchronization, because the voltage in the q-axis is proportional to the reactive power, and then that looks like a reactive power frequency droop control. So that's. I found that quite interesting. Yeah.
Good. Well, then I'm pleased. But I want to put something else in parentheses as well. Sorry, I've just cut you off. There's something about writing papers which I believe let's call ourselves scholars. So we teach and we research. Our job in both dimensions of scholarship is to think about things which might be quite complex and explain it to other people. Explain it to undergraduate students, master's students, whatever. Explain it to fellow researchers. Our job is to explain, not to obfuscate and make things look more complicated than they truly are.
Yeah, and that's I like that. So the reason why I mentioned all that was because you talked about the behavior of the GFM and GFL during faults.
Oh, yes.
And I wonder if the duality concept holds during that half of a second when there is a fault and they both operate differently, because the premise of the duality in terms of the frequency drop looking like a PLL synchronization is that the D-axis voltage has to remain constant and the Q-axis voltage remain 0. But is that true during a fault?
So let's just deal with there's a tie between what we describe as swing. When you perturb a generator, classical one or an inverter, you see it accelerate or decelerate, change angle, basically, according to some relationship, and it's an oscillatory behavior, and your job is to make it lightly damped, your job is to make it well damped, so it quite quickly returns to a stable operating point. And that applies during the fault, so that's the link. When you apply a fault, it is an extreme perturbation. Essentially, if you've got a short circuit fault at the output of the generator, you're preventing it exporting power. Power's got to go somewhere. It goes into accelerating the device, whatever it is. That's the tie. It's so much more difficult to analyze those situations because these, even in a classical machine, but most definitely in inverters, there are lots of non-linear behaviors. And so all of the linear system analysis that we use in lots of occasions goes out the window. Does not apply. It's non-linear, deeply non-linear, strongly non-linear, and so linear models of no help to you. And so it's intellectually challenging. What can you assume stays constant or stays linear? What bits aren't? And you have to model the shape of the non-linearity. And the swing equation is almost always based on some sort of sign relationship. So that's the challenge. I think we've made a bit of progress, but it is impossible to analyze big systems. You can do exemplar small systems, 2 inverters or 2 inverters and a perfect voltage source or something, and analyze that behavior. So it doesn't teach you all you need to know, but it gives you some insights into behaviors, which helps you design. And then to verify the design, you have to go to, well, ideally a physical experiment, but gigawatt scale, that doesn't happen. So you either do lab scale testing or you do very detailed time step simulation, which includes all the non-linearities. But it's an area we haven't got to the bottom of that. There's lots of work still to do. Can I say this? It's slightly less pleasing because it doesn't lend itself to a neat analytical solution. It gets an untidy numerical solution, but that's what it is.
Yeah, but it does give a new perspective, which I think the paper said that was the goal, to help give a way of thinking about these rather obscure concepts.
Yeah.
Okay. So just 1, 2, 3, or 4 quick fire questions just to wrap up the session.
Okay.
And we'll be on time. And just to mention 2 competing technologies, and then you pick one of them and make a case for them. And it may be a bit boring that the first one is GFM versus GFL.
Oh. You've thrown me an oddball one. Because the obvious answer is GFM. I've just said you need them. But I think I'm going to say GFL because most of our power input to the grid will stay grid following, and we want to enhance the grid following with grid supporting features, so we don't need so much grid forming.
Okay. Yeah. Some people have argued that these are not competing technologies; they are complementary.
We need them both, for sure.
Yeah. So we'll have most of the resources connecting to the grid will be grid following, then we'll probably need a smaller amount of grid forming than we would grid following.
Yes, and we have to put a number on that word small. Yeah. That's not trivial.
Okay. Yeah. And then the next one is nuclear plants versus wind turbines.
Oh, wind turbines.
Really?
For sure.
Really? Like we have one here.
We have one here, and it's lovely. I have one in my office still, I think. They're cheaper, they're faster to build, the costs are more certain, and their costs are coming down rapidly with time. We can't ignore the fact that they're variable. I mean, sometimes you talked about popular media and myths and things thrown against us. People pop up and say, "Oh, it's not always windy. What are you going to do?" Like, that's the first time anyone's ever thought about it. Oh, we've been doing a lot of thinking on that. There are ways in which we will combat that. Energy storage in batteries will go a long way to do that. Energy storage in other mechanisms that suit long duration storage will be part of it. And in the short term, we fill in with fossil fuel gas.
Yeah.
And the job is just to drive that down so we use less and less gas to support the wind turbines. Nuclear is not to say it doesn't have a role, but 10 to 15 years to build one.
Yeah.
And all sorts of difficulties getting them off the drawing board into reality because of how expensive they are. Yeah. So we are not going to solve the immediate climate crisis with nuclear. Nuclear will have a role, but we need the renewables more than we need the nuclear, in my humble opinion.
That's good. Interesting. Energy storage versus demand response. In terms of balancing the frequency of the grid.
So this is awkward because I've used this anecdote several times, forgive me. I was in a meeting arguing that it should, we want demand response because there's no capital cost to speak of. You just need to provide incentives to people to use their heat pump or charge their electric vehicle at slightly different times a day. So that's a lower cost route to managing variable resources. And the behavioural scientist in the room came back at me and said, if you had any idea how difficult it is to affect behaviour change, you wouldn't start, you would just build batteries. And if batteries are getting cheaper all the time, then fine, just build batteries. So the answer is you need some of both. But we have been talking about demand response for decades and hardly see it. We should recognise that actually the best sort of demand response is probably electric vehicles. They already have a big battery in them. There's some discretion over when you take energy into the battery to charge it. So I think there will be significant electric vehicle demand response, but batteries.
Okay. And the last one, HVDC versus HVAC.
Different in different parts of the world. That's one of the interesting things about electricity networks. They're kind of broadly the same everywhere, but then have detailed differences. UK will need lots of offshore wind. Lots of offshore wind means subsea cables. For various reasons, impractical to run those on AC. More practical to run them on DC. We will use high voltage DC. And we will use much more of it because we are going to build loads more wind farms in the North Sea and around the rest of the coast as well eventually. And it's a live discussion at the moment, at least in my head, if not anywhere else, is to what point does the system become predominantly DC? So at the moment it's DC as a supplement to the existing AC. Will it ever flip over and that go the other way?
Okay, Professor Green, thank you so much for your time.
You're very welcome.